So as a result of the talks that I've heard yesterday and today, I realized that LSVPs are a hot topic, in particular among this group. So I substantially revised my talk last night. I want to find a way for geochemists and seismologists to actually talk about the same reservoir. And it's difficult, I think, for geochemists to find specific tools to identify evidence of large igneous, the LSVPs and hotspot lavas, but I think we might have a potential tool. I'm going to throw this out today as a hypothesis. It's something I've been talking with Manuel Moreira about for 4 or 5 years now. So just a quick primer. I collect lavas erupted at the Earth's surface at hotspots, and I torture them in the laboratory and purify various elements and measure their isotopic compositions. And I use the isotopic compositions of these lavas erupted at the surface to say something about the composition of the mantle, hopefully the deep mantle. I am an unashamed advocate of mantle plumes. I think mantle plumes make sense. It's a sensible way to cool the Earth and something that's hard to avoid generating at a thermal boundary layer. Mantle plumes originating at the core mantle boundary, which may sample ancient recycled material, possibly primordial material. These plumes melt near the surface, the lava is erupted, and then on top of the plate, and together with the rest of the plate, the conveyor belt continues and slabs go back down into the mantle again. The question is, do we see this material ever again, or is the mantle just a big black box? Fortunately, we have a very nice distribution of hotspots on the map. There are all those yellow points. You might argue which ones are sampling the shallow mantle or the deep mantle, but I think they give us a fairly nice representative distribution of possible compositions in the deeper Earth. So most of us have seen this figure before from Torsvik's Nature paper in 2010. A key feature here that was observed by others, but this is just a more recent figure, is that active hotspots that are thought to have a deep mantle plume-fed origin tend to be associated with the periphery of the large low shear wave velocity provinces, LLSVPs. The big question is, what are these LLSVPs made of? Because hotspots are associated with the periphery of these LLSVPs, it's taken as sort of circumstantial evidence that the hotspots must then be somehow sampling these LLSVPs via plume conduits. So what are they sampling? One hypothesis is that the LLSVPs are sampling primitive mantle material that resides in the LLSVPs. Perhaps they represent the residue of a basal magma ocean, the last gasp, as it were, of a basal magma ocean. The other possibility is that LSVPs are host to a slab graveyard, recycled material that's piled up in the mantle over geologic time. I tend to prefer a hybrid model, but honestly, I don't think any of us know right now. So I've told Stefan this before, and I'll say it for the 6th time. I really like this paper when it came out. Essentially, the idea is that, of course, and we've seen these figures over and over the last couple days, is that a deep basal magma ocean would accumulate dense melt at the bottom of the mantle, and you could potentially have primitive material still surviving at the core mantle boundary. And this hypothesis was then extended in a later paper, which suggested that the primordial helium in neon isotopes in the Earth's mantle might be stored preferentially in the LLSVPs. And this is something that I would really, really like to be able to test. There's no reason for us to believe a priori that helium, primitive helium and primitive neon should be in the LLSVPs. We need some kind of geochemical indicator that's specific to deep mantle melting that we can link to high helium 3,4 primitive helium lavas. And if we can do that, then we can tie this primitive helium signature to the deepest mantle. And I think if we can do that, we can use some recent work by Sujoy Mukhopadhyay, though Manuel tells me it's been done already a decade ago, that the LLSVPs are sampling material from the very earliest Earth. So just a quick primer on primordial helium in the Earth's mantle. We have two isotopes, helium-3, which is much lower abundance, like 1/millionth approximately in the Earth's atmosphere compared to helium-4, which has much greater abundance. Uranium and thorium decay to lead by alpha decay. Alpha particles are just helium-4 nuclei. So helium-4 is building up in the Earth over geologic time. The helium-3-4 ratio in all terrestrial reservoirs has been decreasing with time. Absolute helium-3-4 ratios in the solar system are small, so 10 to the minus 3, 10 to the minus 8. So we normalize the helium-3-4 ratios measured by the helium-3-4 ratio in the atmosphere, so we can deal with nice, normal-looking numbers. Makes it easier to communicate with each other. The solar wind and the atmosphere of Jupiter, for example, have very high helium-3-4 ratios, much higher than anything we found on Earth. And so it's thought that high helium-3-4 represents a primordial, early Earth, solar nebula composition. So before I take us to the next step in this talk, I'm going to assume that the basal magma ocean has crystallized to such an extreme extent that it has reached a eutectic between calcium perovskite and magnesium perovskite, because I'm going to need calcium perovskite to be crystallizing from the magma ocean so that I can have the geochemical fingerprints of calcium perovskite that I think I see in oceanic lavas. Now, the location of the eutectic here is completely unknown. This is a cartoon. I think this is a big problem. The location of this eutectic is certainly going to change with pressure. I would very much like to know where the location of that eutectic is. I think it would then be easier to determine whether or not the basal magma ocean has any probability of co-crystallizing calcium perovskite and magnesium perovskite. Calcium perovskite is the primary carrier of geochemically important elements important because I worry about them. Radiogenic isotopes of incompatible elements like strontium, neodymium, rubidium, samarium. These are preferentially stored in calcium perovskite. So I'm going to worry about calcium perovskite today because I think if calcium perovskite is playing a role crystallizing the basal magma ocean, then we can see these fingerprints in these important trace element patterns. So this is just one example of a partitioning study. There have been multiple studies now, but they all have similar results showing how particular trace elements partition between a melt, calcium and magnesium perovskite at high pressure. And there's sort of a key commonality and takeaway message among these partition studies is that titanium and niobium are very much incompatible in calcium perovskite. So liquids in equilibrium with calcium perovskite should be enriched in titanium and niobium. Also, the key feature here is that you'll notice that magnesium perovskite, most of these elements are all incompatible in magnesium perovskite, but calcium perovskite, you find that many of these trace elements are in fact compatible. But if calcium perovskite were to be crystallizing from a deep basal magma ocean, you'd expect the melt to rapidly become enriched in the elements like niobium and titanium. So I'm going to show you a little bit from a paper that I had 4 years ago that I know that Al Hoffman likes a lot. I'm sorry, Al. Basically, the highest helium-3-4 lavas, the lavas with the highest helium-3-4 are observed from 4 different hotspots, Hawaii, Iceland, Galapagos, and Samoa, all have this peculiar and unusual feature of having elevated titanium anomalies. You can see titanium kind of points up a little bit. It's enriched relative to other elements of similar compatibility, and also niobium, right here, and titanium as well, the sister element of niobium, are much more enriched relative to elements of similar compatibility. Now, it's curious that you have sort of a rough correlation between titanium star. Now, this is just a measure of how enriched titanium is relative to nearby elements. For example, a high titanium star is a large positive titanium anomaly. So if titanium were to plot down here, instead you would have a small titanium star value. So the greater the titanium anomaly in general, the higher the helium-3,4 that you sample. And I think it's very hard to generate niobium and titanium positive anomalies in lavas like this. When I wrote the paper, unfortunately, I proposed two hypotheses. This was sort of a secondary hypothesis. The one I proposed, I think, was wrong, and I sort of have to stand on my head to make it work. I like this idea. I think it helps us make sense of this peculiar geochemical tracer that we have associated with this particular trace element enrichment that we have unique to the highest helium-3,4 lavas. So if we have a calcium perovskite signature, this titanium and niobium enrichment in the highest helium-3,4 lavas, well then I think you have the link to be able to tie the high helium-3,4 reservoir in the mantle to a deep basal magma ocean where you would have melt in equilibrium with calcium perovskite. There are a lot of things that need to happen before this can be more than just a qualitative model. We need to know the location of this eutectic. I'm sure it's easier said than done. These trace element partition coefficients need to be measured at pressures greater than, well, this was between 25 and 30 GPa. So how well do those partition coefficients, how well can they be extrapolated to 120 GPa, pressures of relevance? So Sujoy had this really neat paper come out this year showing that you might in fact have two distinct xenon isotope reservoirs in the mantle that are both distinct from air. Now the key thing about 129 xenon is that it's the decay product of iodine 129, and there's a half-life of 16 million years. So the rule of thumb is 5 or 6 half-lives, you have essentially no 129 iodine left. So all variability in 129, 130 xenon had to be generated in the first 100 million years of the solar system's history. So the first 100 million years after accretion. Now what Sujoy found was that this high helium-3,4 lava from Iceland had a distinct 129, 130 xenon relative to Morp. Now if the high helium-3,4 reservoir, which this lava samples, is located in the LSVP, which I think you could make a case for based on titanium, tantalum, and niobium enrichment in ocean island basalts, then I think you might be able to also make the case then that the LSVPs are old. So there's a lot of links, of course, that you have to make there, but I think so far this is about as close as geochemists can get to saying something about the composition of the LLSVP in ocean island basalts if they're sampled by ocean island basalts and natural samples. So I'm going to transition here from discussing whether or not we have primitive material in the LSVPs to talking about whether or not hotspot lavas sample materials that were once at the Earth's surface. So can these deep mantle reservoirs host material that was recycled or sent into the mantle from the surface in deep geologic time? So I'm going to use clues from sulfur isotopes here. Here's an example of, well, this is a compilation showing cap delta 33s, so non-mass dependent fractionation of 33s relative to 32 and 34s. I'll show you in just a second. Showing this in natural samples, terrestrial samples from 3.8 GA to the present day. And you can see at about 2.5 GA, things essentially flatline. You don't see variability in cap delta 33s. But before, 2.5 GA, there's significant variability in cap delta 33S, and I think that by looking for cap delta 33S anomalies, which were generated uniquely in the Earth's atmosphere before 2.5 billion years, then, well, you'd have a timestamp. If you could find this signature in oceanic lavas, you'd have a timestamp for when the material was recycled into the mantle. And you'd also have a certificate that the material was once at the Earth's surface. So here's this, just trying to keep this isotope light, but maybe some of you might find it interesting to see what this cap delta 33 sulfur actually means. So in a delta 34 versus delta 33S plot, where here's delta 34S defined, everything in the Phanerozoic and Proterozoic, the last 2.5 billion years, plots on or very, very close to this particular line, the mass-dependent fractionation line. Samples before 2.5 billion years, however, can plot both above and below this line. Samples that plot below this line are depleted in 33 sulfur, and so have negative cap 33S anomalies, and samples that plot above that line are enriched in 33 sulfur relative to 32 and 34, and so have positive cap delta 33S signatures. So here's an idea of what the Archaean sulfur cycle was thought to look like. You have your multiple sulfur species in the atmosphere, which are all being bombarded by deep ultraviolet because you have an oxygen-free atmosphere, so you have no ozone layer. And what you end up with is photolysis of these different sulfur species, and the reduced species, as a result of this photolysis, end up with positive cap 33S anomalies, and the oxidized species have negative cap 33S anomalies. It's based on the geologic record. It seems that sedimentary materials tend to have the positive cap 33S anomalies, and materials associated with marine oceanic crust would have negative cap 33S anomalies. So if you were to if these were to have been sent down into the mantle as a subduction package during the Archaean, or perhaps before, and if this material was then preserved somewhere in the mantle, most conveniently, I think, would be in the deep mantle, where convective motions are presumably minimized, well, then you'd have a way to preserve this material, and perhaps you could sample it in a hotspot and see these sulfur isotope anomalies in the present day. This is exactly what James Farquhar found in his 2002 paper in Science. He looked at diamond sulfide inclusions trapped in diamonds, and he found that these sulfides have small but measurably positive cap delta 33S anomalies. Now remember, the positive cap 33S anomalies are associated with Archaean, crustal, and sediments. James Farquhar's hypothesized that the complementary negative cap 33S anomalies would be found in subducted Archaean oceanic crust. So let's find where this negative cap 33S anomaly is. Where can we find evidence of ancient subducted oceanic crust? Well, I think there's a certain species of hotspot lavas in the South Atlantic and South Pacific that sample ancient recycled oceanic crust. It's been proposed for a long time now, for several decades, that lavas with this particular flavor sample ancient recycled oceanic crust. Here's the one island that we went to in the South Pacific, Mangaya Island and the Cook Islands. Here's New Zealand and Australia and Samoa for reference. Mangaya Island was at one point completely submarine, and it represents the oldest oceanic lavas exposed. So they're pretty crummy overall. There are only about 4 outcrops you can go to find relatively fresh lavas. Otherwise, most of the lavas have been weathered to this reddish clay soil. So my student crushed around 5 kilograms of material and pulled out olivines from all of this material and looked at each olivine under a binocular microscope and exposed the biggest inclusions. And over the course of about 3 months, she found hundreds of sulfides, but they were all tiny, too small really to do much with. But she found 2 large sulfides. Here's one that's maybe 80 microns, 100 microns. This one is well over 100 microns. And we measured 3 sulfur isotopes on these sulfides at the Norrbotten facility in Stockholm, Sweden. And 10 measurements on each of the 2 sulfides, averaging them together to beat down error bars, and we find negative, small but resolvable negative Cat 33S anomalies. Now, here, just for comparison, are James Farquhar's measurements from his 2002 science paper. And here's what's thought to be an average upper mantle or more mantle crustal signature. You can talk to Gibran for a better estimate. He sees some variability on this axis for delta 34S. So, of course, pretty excited about this result. We'd certainly like to find more sulfides. We have this particular sulfide. These 2 sulfides were from 2 different hand samples. Olivines recovered from 2 different hand samples. The olivines, sulfur is incompatible in olivine, so the sulfur in a pure olivine separate should be tied up primarily in sulfides hosted in the olivines. So I picked half a gram of olivines, and James Farquhar ran them and found a small but resolvable anomaly in the olivines. So right now, James is going to make 5 more measurements of olivine separates from lavas from this hotspot, and we hope to see more variability. But yeah, this, just to be sure that the sulfides represent the same composition as the whole rock lavas, we measured lead isotopes in the 2 sulfides, and they're the same as the whole rock lavas from the island. So this peculiar sulfur isotope signature is associated then with the lead isotope signature that we think represents ancient recycled oceanic crust. So I think this is really a really important step forward for placing time constraints on mantle recycling. If you really can send material down into the mantle in the Archaean and preserve it for 2.5 billion years or more, we find that we can then sample this material again in hotspot lavas that are relatively young, 20 million years old. So I think by finding these kinds of anomalies, then critically you can place a timestamp on the age of different mantle reservoirs, whether they formed before or after 2.5 billion years. And it's a certificate as well that these reservoirs were at the surface before 2.5 billion years ago. So it's giving you strong evidence of recycling, and it's giving you also a timestamp. I think of this as the equivalent of beryllium-10 for hotspots. And just again, James was amazingly prescient to realize that this negative 33S sulfur signature could potentially reside in deep mantle lithospheric graveyards. So that the complement to the positive 33S anomaly found in diamonds could reside in these ancient slab piles at the bottom of the mantle. So I guess in summary, I think we might have evidence to tie the high helium 3-4 signature to the deepest mantle where melt would be in equilibrium with calcium perovskite. There are some trace element signatures in high helium 3-4 lavas, unique to high helium 3-4 lavas, that are really hard to generate. And I think calcium perovskite might be a way to do this. Sulfur isotopes I think it's a harder sell to say whether or not these strange anomalies found in the diamond inclusions and the ocean island basalt sulfides represent preservation in the deepest mantle, but certainly I think the deep mantle, perhaps the LLSVPs, represents a convenient location for long-term storage of this sulfur isotope signature. So thank you very much.